There's some topics in here that you're just going to have to trust me, and I'll try to kind of emphasize what's going to be on the test. Kind of do it that way. But I can see when I talk about, does this look familiar? This is Hubble's law. You know, the whole looking at galaxies. Those dots are galaxies. And along the x-axis is how far away they are from us. Along the y-axis is how fast they're moving. So I can see that I don't ever say how they use this, or I don't say what the age of the universe is. But I did in review session. And didn't I say something like 13 to 15 billion years? Actually, it's on your review sheet, billion years old equals age of the universe. And I'm going to try to kind of talk you through how we can use this motion of the galaxies to backtrack to how long ago our universe first started. Okay. But this works pretty good. See what you guys think about this little animation. Once you write down what you need to. This is new stuff. I added that just this afternoon. Do you see the we call it y is equal to mx plus b. That's the equation for a line. So I'm taking all the math out, but I just, in my own mind, tried to kind of organize that idea about a line. And of course, the y is velocity. The x is actually distance from the Earth. Okay, and the m is the slope of any line, and the slope is the h0. That's Hubble's constant.
Well, we need to know that. Like, should we write that down?
No, I don't think so. You can go back and listen to it if you want to. But it was just for me to kind of convince myself that actually we can get to basically time. We can get to time, which corresponds to age, if we take the distance divided by the velocity, which is basically 1 over the slope, or 1 over h0. So age is 1 over Hubble's constant. Okay, that's kind of
so
how
the
that
distance
works.
Divided by the velocity is the time. Is that what you're saying?
Mm-hmm. Yep, and that's kind of like if you were going 5 miles and you know that you were going to go 10 miles per hour. Actually, you know that it's going to take you a half an hour to get there. 5 divided by 10 is a half. Does that make sense? Yeah, that's kind of so. But let's see if this works for you. This is adorable. Those little things that look like rat pellets are galaxies. I know, mouse pellets. Those are galaxies. And it's kind of alluding to something we're going to talk about more after your test, which is the Big Bang. Basically, if things are expanding now, what this little video does is, well, what happens before the expansion? So basically rewinds the clock. Okay, so here the G stands for giga, big M stands for mega, big G stands for giga, so giga years. So basically we're going back in time. Okay, so if it's expanding now, then what it used to do, or going back in time, we would make it smaller. Okay, so obviously then, if we keep that thought going, basically all of the galaxies used to be one big lump, small lump. I don't know. Again, we're going to talk about this. You know how we call a black hole singularity? They call the thing that our universe unfolded from also singularity. Singularity. I know, it's amazing. Okay, so that's kind of how that goes. Whoops. Go back to the slides. Let's see if this does it for you too. And actually, I think this is this would be good to kind of think about for next week too. This is going the opposite direction. So if I hit play, okay, so one scenario is basically we are kind of in the center of all the expansion, but things don't really add up because we really don't see an edge. Another scenario is this. And one of the things we're going to talk about next week is something called inflation. And inflation basically said you had singularity, all the stuff that's going to make your little universe, and inflation said basically with zero time, it went to this, okay, that you see here, and then it's been kind of expanding ever since. Actually, not just expanding, but accelerating. Oops, that isn't what I meant to do. Okay, so in that scenario, the little hash marks, by the way, is the fabric of space and time that Einstein talked about. Okay, so basically, it's not just that the galaxies are moving farther from us or moving away from us, but the fabric of space and time is getting larger. So yeah. And no, you won't have to write an essay on that on your exam. So that's all good. And it didn't make it to this test, but sometimes I'll put it on a test because this concept of the cosmological horizon, it's just poetic, I think. And basically the cosmological horizon is, like this says, the edge of what we can see. So there's a problem with the Big Bang. Our universe began maybe 14 billion years ago. Let's split the difference between 13 and 15. 14 billion years ago. So even if an object was bright enough, do you see where we could not see, there should not be an object that's, for instance, 17 billion light years away. There just should not be an object there. Okay? We should not see one there because light hasn't had 17 billion years to get here. Does that make sense? Oh. So it's just interesting. So this actually is kind of a common thing to talk about, where if you think about a balloon doesn't really have an edge, it's all one kind of sphere, okay? And just kind of like the fabric of space and time is expanding into nothingness, okay? And there's no edge to it. Let's see if it, oh well, that's okay. So one of the things that needs to account into our understanding of how our universe began is the fact that even though it looks like the universe is lumpy to us, the universe is pretty homogeneous. It's pretty similar throughout. The universe is. And that's significant to being able to kind of put the pieces together. So here's one to kind of, I bet you'll buy into. So this is talking about look back time. And here's the deal. These two spiral things, this one is the Milky Way, okay? This one over here on the left. This one is just some pretty galaxy of interest. And that little poof there is a nova event, okay? And so 400 million years ago, the nova, a star, a nova would be repeating, right? Let's make it a supernova. The poof is a supernova event. Star blew up, okay, 400 million years ago. But did we see it? No. So 400 million years then lapses, okay? So now that now that galaxy that it occurred in is over here, okay, but we see the event from over there. Does that make sense? Because that's where the light's coming from, even though now it really is, it's changed its position. Okay. Oh, I guess I didn't catch this. This is, it's like light traveled in all directions, okay, but actually the light that we finally see is, we catch up to it. That is so bizarre to me. Does that make sense to you? Because everybody's moving. Let me go ahead and put this whole thing up here. Everybody's moving. Okay, so it started here. It went in all directions, traveling the speed of light. Okay, but notice we couldn't catch it here because, you know, it's just, it took a while to get there. In the meantime, we moved, okay, and eventually it coincided with, you know, this energy that went. In the meantime, it's now over here, okay, but we still see it right there. Like, okay, so I guess the term "just get over it" kind of applies here. Okay, so astronomers need to be able to sink their teeth into something, and so basically, from what I understand, they just say, they call the event or the galaxy or whatever in the place it is. They don't say now it's here. They say it's right there, even though it really is somewhere else now. Do you know what I mean? Yeah.
So we are seeing today the super, or the, whatever you called it, as it was 400 million years ago when it blew up. Is that what it means?
Right. So this is the delay. You know, it's definitely delayed. You know, we knew that. But not only is there a delay when we get it, but with this expanding universe and all galaxies moving away from all other galaxies, now we are in a different position.
Right.
Yeah. So we map out things as they appear.
Why would that not travel with?
Well, here's another, maybe this will help. So up here, now the galaxy continues, you know, all those stars in that galaxy are just shining away, okay? But we're not going to be able to see the energy that it puts out right now until another, you know, 400 million years. And by then, it will be somewhere else. It's like, so, no. So, expanding fabric of space and time. We have yet another red shift going on, and this is associated with the fabric of space and time getting larger. I think of it as that way. And so actually there's an elongating of energy. And that's called the cosmological redshift. It doesn't have to do with Doppler effect. It's just the fabric of space and time expanding. Okay. And that term didn't make it on the test either. But this concept sort of did. So if we're okay with the fact that if we're gathering photons or looking at an object that's farther away, we're seeing the baby picture, that sort of thing. In order to understand how galaxies kind of start out as babies and grow up, all we got to do is look at a galaxy far away, look at a galaxy a little closer, look at a galaxy a little bit closer, and then we got a sense for kind of how they evolve. Okay? So that's kind of what this is. From left to right, actually what this is about how long after the universe unfolded were these pictures taken. Right at the kind of the cosmological horizon. So these would be pushing, 15 billion light years away. That's what these galaxies look like. Remember I said those galaxies look like they may have been early ones? Okay. So these would be kind of irregular galaxies, kind of over here. Elliptical galaxies, kind of showing you from the baby pictures to kind of a more mature elliptical galaxy. Okay, spirals, kind of the baby to the more mature. Okay. One of the things we're going to talk about next week is that, early on in the history of our universe, how quickly stars were born and lived their lives and died at just a crazy rate, very fast. Okay, so things have kind of slowed down. And then down here, we kind of have an assortment of irregulars. Okay. So, a galaxy, how does it form? Well, it forms from a cloud. Okay. And actually, we kind of talked about this, the formation of the Milky Way, a little bit, I think. It's got to be a bigger cloud than our solar nebula, right? A bigger cloud than just makes one star. Because this would be a bunch of stars being made in a galaxy. This last one here, actually, this is kind of with no definition. This is kind of, you see a little bit of budding here. And here you kind of almost see kind of that fragmentation we talked about. A bunch of stars to be born as a star cluster. In this case, a bunch of stars to be born as a galaxy of stars. Let's see, let me go back. Okay. So the term protogalactic cloud actually is a term on your unit exam. And it's like a prototype means the thing before the real thing. So a proto-galaxy or protogalactic cloud is the thing that's going to become a galaxy. Not many heavy metals there. So I think this should be true of any galaxy. And we were talking about this before class. It seems like the Milky Way galaxy should be kind of similar to all of the other galaxies that were formed at the time of the Big Bang, you know. But we kind of have that look back thing going against us in that when we look around, when we finally get the light from those distant galaxies, those are kind of baby pictures of those galaxies. We do look kind of similar to Andromeda. So the term conservation of angular momentum, where you draw matter in and it goes faster and faster. Notice we're going to see here in a minute that some galaxies had more spin or more angular momentum than others. We think actually that spiral galaxies had more spin or angular momentum than elliptical galaxies. Just very pretty pictures. So there's the Hubble tuning fork. There's the handle and kind of the little prongs out there. So we have our ellipticals, spirals, and barred spirals. And so if we just kind of talk about spirals and barred spirals and ellipticals, we can kind of draw some just general conclusions. So the tracks that you're seeing, and I think I'm going to play this animation, it's pretty good. This actually, over here, is the track showing ellipticals. Ellipticals. And these are spirals, whether they're barred spirals or regular spirals. All right. So from left to right, you see actually this is going to end up as elliptical. This is a spiral. This has less angular momentum. This has more angular momentum. See if I can start them at the same time. Oh, that one. Okay, elliptical galaxy. Now that's a galaxy of stars. This has more spin to it, more angular momentum. As I understand it, these elliptical galaxies that don't really have a disk component per se, they're all like the spheroidal kind of thing going on. That haze you see actually is just, it's not dust, it's stars. So this actually is showing you, comparing the density of the two. So there's your ellipticals and there's your spirals. Spiral galaxies are generally less dense, although you can have kind of sparse elliptical galaxies. So they're not as compact and they had more angular momentum to start out with. Okay, so again, ellipticals or spirals, they differ in angular momentum and density. This didn't make it your test either. All right. And I was trying to, this distant red elliptical galaxy, is it red because it's the cosmological redshift, or is it red and it's far away, or is it red because it's far away and it's moving faster than anything else? The redshift? I don't know. So you're going to see this slide a couple of times, and can you see the hearts of two galaxies? Okay, like there's the heart of one galaxy and there's the heart of another galaxy. One of the things we're going to kind of end this chapter on galaxies is to say that, like the middle of the Milky Way galaxy, most galaxies have a black hole. Okay, so as galaxies interact, there's a different possibilities. And this did make it to your test. So one of the things early on is that the interaction you just saw on the previous slide, kind of the, I think they might call that kind of the cat's tail sort of feature, structure, even though there's actually two galaxies there. Those collisions actually happened more early on than they do now, and it makes sense because they were closer to each other. So I'll put test. Q. Okay, collisions were much more likely because they were closer together. Expanding universe and all that. Okay, so these are kind of some of the kind of irregular shaped galaxies we see when we look back in time, looking far away. And so kind of couple the last slide, the previous slide with this slide. I mean, its collisions are possible. It's kind of like, they look like they've been beat up. So this again is that same slide with these two galaxies that are interacting. And actually, one of the things, positive things that interactions can do is actually birth new stars. So you can kind of see the two frisbees, the two kind of yellow centers are the centers of the galaxies, and kind of the dance they do over time. Although this takes a long time to occur. Speaking of time. Good Lord. What do we have, 19? No, that's 14. Okay. Because this actually, it's not very long, but this sometimes comes up. I'll probably quote this in a video. We call this a merger. They would call that actually cannibalism. They do. Galactic cannibalism.
It's never happened before?
I know, like, a big one has basically taken over a little one before. I think I've read that. And kind of what you're saying, though, I don't think, like, the entire thing has gone down the drain. But the last few slides, we're going to talk about when a galaxy is feeding, when the black hole in the middle of a galaxy is feeding. So, I don't know. So, let's see, collisions. So I was glad we watched that video because I guess I didn't realize that you can get elliptical galaxies out of, for instance, two spiral galaxies combining. Makes sense. That's kind of neat. So this is a cluster of galaxies, and actually it's the same one. If I were to go back a slide, it's the same field of view, but the other one is much prettier. That's like the visible light, and this actually is in, say, X-rays or something. Okay, so you see the hearts of the galaxies. So this is a galaxy, this is a cluster of galaxies. So each of those little orbs is an independent galaxy. So that's a big honking one at the center. And it's kind of like what you were saying. It looks like that center one's gobbling up everybody in its neighbor. And if you think about, like Einstein says, gravity is basically an object making a dent in the fabric of space and time. That's kind of what it is. So it's like, oh. So, I don't know. Okay. So different kind of cute little names given to different subtle differences in galaxies. A starburst galaxy is being shown here, and it kind of lives fast and furious and kind of dies out young. So that's a galaxy, kind of a small sort of galaxy. That's the same galaxy, but looking at it now in a different wavelength. So this says it's looking at it in X-rays instead of visible light. So we just get different information. Like we didn't see those little, this is a galaxy again, galaxy of stars. So we didn't see those little hot spots in there until we changed wavelengths. So I'm going to go ahead and add something to this slide because we're finishing up here, aren't we? I think we are. Quasars, actually, I'm going to go ahead and say, are from black holes. From black holes. If I put BH, hopefully you guys know that's black holes. Not just any black holes, but they're from what we call supermassive black holes. And supermassive black holes are in the center of galaxies. The type 2 supernova explosion leaves a black hole or a neutron star. That black hole, if it is a black hole, is called a stellar black hole. Stellar, get it, star, stellar. This is called a supermassive black hole. So quasars. And I think we saw a video not that long ago that said quasars are like quasi-stellar objects. And they're a lot more energy than just an individual star. So these highly energetic events, you know, we said that it's kind of like the whole lighthouse and candle. I mean, they look the same to us, but the lighthouse was further away. And so the deal is we see these, how do I say, these events happen way far away. And the fact that we can see them all must mean they're very energetic. And this is actually kind of emphasizing how far away do we see them. Well, we see just crazy, great, highly redshifted quasars. And actually, if you watch those documentaries on how we can die, energy from a quasar is 1. Okay, so a quasar, again, it's a feeding supermassive black hole. It's a highly energetic event. And from what I understand, you basically, if it's a feeding black hole that's part of a spiral galaxy, you kind of see the quasars as jets. You've seen that word here on these last few slides, jets of energy kind of coming outside. Like if this is the Frisbee part, okay, they come like that. Disturbed galaxy, that's pretty.
Just eat stuff, right?
They don't eat at all. Okay, basically.
Eat, I mean.
Oh, yeah.
That's what I meant.
Black holes.
Yeah.
Yeah. They go through active periods, and then I think the slide says basically ours is kind of in a quiet period. Our Milky Way black hole, Sagittarius A star, it's kind of really, but they go through periods. So this is kind of looking at the different types of energy that's emitted during a quasar event. I think it's neat because if you were taking this course maybe 15 years ago, they wouldn't have pinpointed where that energy was coming from. So what you're looking at, what I tried to explain as far as I know it, is basically the disk of the disk is right here. Okay, so here's halo region and halo region, and these are the jets of energy. I should change my color, shouldn't I? These are the jets of energy kind of shooting in both directions from the disk. Now, it's kind of, this talks about radio galaxies, blah, blah, blah. But the few slides, if you read them, it just says that radio galaxies are kind of tamed down. The energy is tamed down into that longer wavelength, radio waves, right? Because kind of the dust and gas that are associated with that galaxy. But it's really a quasar that's kind of tamed down. So anytime we say a galaxy is being active, okay, kind of think quasars. It's radio galaxy, but, and this is kind of trying to show you kind of over time the blobs of energy that's coming out. So the way this works, if these are the jets of energy, okay, kind of the center is, you know, the disk that's kind of shooting in both directions. Not sure if this is an artist's rendition or if this is a real thing. But again, radio galaxies are an active galaxy. But like I said, we don't get all the brunt of its energy. So active galaxies. Besides, I'm going to add something here. Think quasars. Okay, so I think my slides are a little bit backwards because I feel like if only finally right here do I say those quasars and radio galaxies that kind of have lobes of energy coming out, you know, kind of perpendicular right angles to the disk. That's associated with kind of the commotion that the black hole is creating. But now we talked about this. Remember that if it's anything energy or matter, if it goes past the event horizon, it's never going out. Okay, so this actually uses the word accretion disk again, stuff that's queuing to go down the drain of the black hole. This just talks again about the accretion disk. It's funny because I'm kind of like at this point in the lecture, you're like, you believe that, I mean, you buy all this, that this energy is coming from a supermassive black hole. But mathematically, it works out to making sense if you're an astrophysicist. So that jet of energy, we would call that a quasar.
What did that say?
Jet of energy. I know, I couldn't read it myself.
Quasar.
And then jet of energy.
I was like, I don't see it at all.
I totally got that.
All right, so actually this is a deja vu slide. And this was looking at Sagittarius A star. It's kind of where the plus is. I'll just put SAG A star. Okay, and those little colored balls are the paths of stars as they orbit Sagittarius A star. And so that's how we know how massive that object is. So kind of related to that, I was looking at this at my office and I didn't check it, but check it out. But actually, this blue shift right here, okay, that must be it coming towards us. And we can look at how much it shifted so we can get a speed on it. And actually the other one is red shifted, so it's going away. Okay, so actually this is how we can get to the amount of the speed of everything in another galaxy. And if we can get just like our own galaxy, if we can understand how the stars are being influenced by the mass in the center, we can get to the mass in the center. Okay, so that then mass must be an object that weighs, that has a mass of 3 billion times the mass of our sun. And so again, when you take the mass and you know how much area, or excuse me, volume it covers, okay, it must be this scenario over here where it's dense enough, it's got to be a black hole. So this says the nearby galaxies and maybe all galaxies have a black hole. And I like this term, you know, just like for future reference, if you hear anybody talking about, like I think I said, a supermassive black hole, that's the one in galaxies. A stellar black hole is the one, now it seems so dinky, right? Stellar black hole is the smaller one, just a massive star, that supernova type 2.
Supermassive.
Supermassives can go through an active stage and have quasars, yep. But not all supermassive black holes. Some are quiet and some are active. Yep. So this then is kind of a scary thought. This basically says for your galaxy that has a supermassive black hole, this kind of makes sense, I guess. If you look at the size of the nuclear bulge, okay, the larger the nuclear bulge, then the more massive the supermassive black hole in the center. Makes sense. And this actually is a kind of a fun slide. So for whatever you think of black holes, good, bad, or otherwise, don't want to be spaghettified, right? They happen to probably be very necessary mechanism in the evolution of galaxies, and of course that means stars and planets. And so a necessary evil. Very good. So, like I said, I will post, might be on my YouTube. I'll probably send you a link to the video that we might have finished watching. And also a link to the video for the review session. Okay?
Okay. And then the
Yeah.